Hello, everyone. Thank you for joining us. Today we have Yunshu Liu presenting his research. Liu is currently a PhD student in information engineering at the Chinese University of Hong Kong, supervised by Professor Jianwei Huang and Manhong Chen. His current doctoral thesis theme is on the incentive mechanism design for blockchain systems. His research interests include the field of network economics, game theory, and control theory, with current emphasis on blockchain and its applications. Without further ado, let's welcome Yunshu Liu for his presentation today. Thank you.
Okay, thanks. So today, the title of my presentation is Incentive Mechanisms Design for Sustainable Blockchain Storage, which is part of my research project during my PhD study. So the blockchain system has been applied to many applications, including supply chain, finance, energy, and traffic, because of various properties of the blockchain. For example, the decentralization, transparent, and verifiable, and so on. However, with the booming of the blockchain system, it has also suffered from its storage sustainability issues. On the one hand, the miners are bearing huge storage costs. For example, in July 2020, a miner stores all data in the Ethereum blockchain can cost up to $2,000 per month. And almost all the data are transactions, which is denoted as TX in this talk. So the total storage cost of all miners can cost more than $20 million per month, because there are many miners in the system. However, on the other hand, the miners are receiving insufficient transaction fees from the users. During the first half of 2020, the monthly average transaction fee is about $2.9 million, which cannot cover the storage costs. So this causes the storage sustainability issue, where it is insufficient transaction fee for storage costs in the blockchain. And this issue has contributed to the loss of the miners in Ethereum since 2018, and it has lost about 2/3 of the miners. And this will also jeopardize the system security in the long run, as there are less and less miners. There are fewer and fewer miners in the system. So regarding these issues, there's also some related works. So the existing works mainly focus on directly reducing the storage cost. They have proposed multiple methods. For example, the sharding, where they divided the blockchain into multiple parts, and each miner only need to store part of the transactions. There's also some pruning method, where they directly reduce the time of storing a transaction. So after a certain time, the transaction will be removed from the blockchain. There's also some compact design to directly reduce the size of transaction or a block. However, despite those research efforts, our analysis in this talk will show that directly reducing the storage cost does not necessarily guarantee the storage sustainability. This is because when they have lower storage costs, users will also pay lower transaction fees. So the transaction fee may still not be able to cover the storage costs. So the motivation of this work is to design incentive mechanisms to encourage users to pay sufficient transaction fee to achieve storage sustainability, where the storage sustainability means that we want the total transaction fees to be able to cover the total transaction costs of transactions. First, we give the overview of this talk. So because there are different users' behavior in the blockchain system, for example, there are a few busy smart contracts. They generate a sufficient fraction of transactions. For example, in April 2023, a smart contract called Uniswap that generates about 10% of all Ethereum transactions. And on the other hand, the majority of the users generate transactions at a relatively low frequency. So during the same period, the Ethereum monthly active users, there are about 15 million of them, which is quite large. But on the other hand, the daily active users, there's only about 0.4 million. So majority of them only monthly active and generate transaction at a relatively low frequency. So because of these drastically different behaviors, we consider two settings. In part one, we consider the heavy user settings, where for the heavy user, each will generate many transactions corresponding to the first scenario of the busy smart contract. In part two of this talk, we will consider the light user setting, where each user generates one transaction corresponding to the second scenario. Okay, so first, let's begin with part one. In the part one of this talk, we want to answer two following key questions. First is, why are miners willing to include the insufficient fee transactions in blockchain and causing the storage sustainability issue? And with that, after we can understand why such an issue exists, we can design a storage sustainability mechanism for the heavy users, where we want the transaction fees to be able to cover the storage costs. Okay. So first, we describe the system and propose the model regarding it. So for the blockchain system, there are three agents involved in the system. First is a protocol designer who will propose the mechanism for the blockchain system, where we consider the protocol designer design the mechanism, and his objective is to maximize the social welfare of the system, which is a sum of users and miners payoffs. And on the other hand, we want the mechanism to be able to guarantee the storage sustainability. After the protocol designer designs the mechanism, the users will generate transactions and pay the transaction fees. So they will trade off between the transaction fee, which is a payment for him, and the waiting time. In general, if a user pays a higher transaction fee, he will bear a lower waiting time, and vice versa. So he will trade off between these two factors. After users generating transactions, miners will include those transactions into the blockchain. So they will select the transactions to include in the blockchain, and they will trade off between the transaction fee, which is a reward, and the storage cost. So miners are more willing to select the transactions with higher transaction fee and lower storage cost. Based on the system, we can propose a three-stage Stackelberg game regarding this interaction. So in stage one, it's the protocol designer's mechanism design, where his objective is to maximize social welfare and guarantee storage sustainability. So then the mechanism, under the mechanism, the user is in stage two, proposing the transactions. There are totally n users proposing transactions and set the fee. So in stage three, there's miners selecting transactions, where essentially they will sell the storage of the blockchain back to the user's transactions. Okay, given this system model, we will introduce and analyzing the model backwardly because of the backward induction. So first, we will introduce the stage 3, which is minors transaction selection. We consider totally m minors, each with a mining power of alpha m, representing the probability of successfully mining a block in the blockchain. So the strategy of the miner m is denoted as xm tau, representing that when mining the block tau, the miner m will select a set of pending transactions to be included in the blockchain system. And here we use a figure to illustrate the miner's strategies. When mining the consider when mining the block 1, there are 3 transactions in the pending transaction pool: transaction 1, 2, and 3. So consider there are 2 miners, and miner 1 select transaction 3 to be included in blockchain, and miner 2 select transaction 1. Suppose miner 2 mines the next. Suppose miner 2 mines the block 1, and then the transaction 1 is recorded into the blockchain, and every miner needs to store the block to reach consensus. So since transaction 1 is in the blockchain, it can be removed from the pending transaction pool. So there are only 2 and 3 transactions left. Again, the miner 1 is try to include the transaction 3 into the blockchain, and this time he can get the block. So the transaction 3 will be in the blockchain. Oh, sorry. Okay. So based on this illustration, we will find that when miner 1 finds a block, miner 2 also needs to store the block to reach consensus. So this leads to So this leads to the following observation regarding the blockchain, regarding miners transaction selection, which is called the negative externality of the transaction selection. We find that a miner's transaction selection will impose storage costs to other miners. So for example, here, when the miner 1 finds a block, including transaction 1, miner 2 also needs to store the block and bear the storage costs. And this will be a key observations in this part 1. So based on miner strategies, we define their payoff as follows. So for all the miners, for miner m, his payoff during mining the block tau is as follows. So there will be 2 situations. When miner m finds the block tau, he can get the transaction fee and bears the storage cost, where the probability of finding the miner m finding the block tau will be alpha m. And when he finds the block, he can get the transaction fee F&K from his strategy selection, and also he needs to bear the storage cost CS for each transaction. So CS represents a homogeneous storage cost per transaction to any miner. And in part 2 of this talk, we will generalize this homogeneous storage cost assumption. But here we currently focus on a simplified version, which is a homogeneous cost. And this also reflects that each miner needs to trade off between the transaction fee and the storage cost, where transaction fee is a reward and the miners try to get more transaction fee. And storage cost, the miner try to get lower storage costs. There's also another case where when the other miner I finds a block tau, the miner m also needs to bear the storage costs. This is exactly because the negative externality of the transaction selection. So this happens with probability alpha I, and the miners need to bear the storage cost CS for all of the miner i's strategy. So the minor m's payoff will be sum of these two parts. So based on this model, we can analyze Nash equilibrium of the stage 3. So under the Nash equilibrium, all the minors get the highest payoff. So even though he can deviate, he cannot increase his payoff. So we denote the index of the highest fee transaction as I star. So the theorem 1 summarizes the stage 3's Nash equilibrium. So specifically, the minor m will adopt the following strategy during mining block tau. So if the transaction fee of the highest fee transaction is higher than CS, then the minor m is going to select the highest fee transaction. But if the highest fee is smaller than CS, the minor m will select no transaction. And theorem 1 is the answer of the key question 1, so which is the reason of the storage sustainability issue. So from the theorem 1, each miner's fee threshold of admitting a transaction is CS, which is a transaction storage cost to one miner. However, this cost cannot cover the storage cost of all miners, which is M multiplied by CS. This is exactly because each miner neglects the negative externality of transaction selection. So he will select a transaction that can cover his own storage cost. But the transaction can cover his own storage cost, may be far away from covering the storage cost of all miners. Moreover, we find that directly reducing the storage cost CS, this will lower miners' fee threshold of admitting a transaction. So the transaction fee may still not be able to cover all miner storage costs and achieve storage sustainability. Next, we will introduce the stage 2, which is user's transaction proposal. So we consider there are n heavy users, each generates transactions following the Poisson process. His strategies is denoted of user n, denoted as lambda n, which is a vector comprised of lambda ni. It represents that the user n strategy is to set the transaction generation rate at each fee choices fi. Fee choices fi are set by the polygon designer. There are totally I of them. And the user n will generate a sequence of transactions denoted as transaction nk, where k takes a value from 1 to the infinity. So then we will illustrate the user's payoff. We first illustrate the transaction proposal process, which is forming a transaction queue. Suppose there are two users, each will generate transactions, and the index here will denote the transaction from user 1 or 2. So their transactions will enter in the pending transaction pool, and they will pay the fee to the miners, and miners will include those transactions into the blocks. So the user's transaction proposal is the transaction of arrival, and the miner's mining process will be the transaction departure. So this will forming a transaction pool. Forming a transaction queue. Based on this, we can derive the surplus from a transaction nk, which is a case transaction from the user n. Surplus is denoted as theta nk. It includes two cases. If transaction nk is included in the blockchain by the miners, the user n can get the Rn, which is called the transaction on-chain utility. And we consider there are two types of users. There's type H has high utility and type L has low utility. Moreover, the users, when the transaction is in the blockchain, the user needs to pay the transaction fee, FNK, the miners. He also bears the waiting cost from the transaction queue, where the gamma here represents the impatience level, characterizing the waiting cost per unit of waiting time, and WNK represents the waiting time. So each user will trade off between the transaction fee and the waiting cost. The second case is if transaction NK is not included in blockchain, then the user only bear the waiting cost, which is minus the gamma WNK. Under this case, the waiting time will approach infinity. Next, we introduce the waiting tax for transaction NK. This is assigned by the protocol designer and is one of the key design in our incentive mechanism. So let's revisit this transaction queue figure. We will find that if user 1 generates many transactions, so the miners will be busy processing user 1's transactions, and user 2's transactions will wait a long time in the pending transaction pool. So under this case, we will find that a user's transaction proposal will increase other transactions' waiting time. It's like if there are, it's just like a traffic scenario. If a lot of people driving their cars on the road, then it will increase others. Waiting time. So we will propose the waiting tax to let each user pay for others' transaction congestion. So there are the user N will pay the waiting tax Pni, any user I, and there are 4 cases of them. So consider for a type H user, he will pay the waiting tax PH to another type H user. He will pay the waiting tax PHL for another type L user, and so on. And this model is still generalized enough to characterize current blockchain practice. If we consider the 0 waiting tax, this is just the current blockchain practice. So based on this, we can define the time average payoff for the user N. It comprises of the surplus from the transaction NK and minus the waiting tax paid to others. And also need to add the other users' waiting tax that pays to user N. So based on this model, we can derive the Nash equilibrium of the stage 2. Consider the fee choices of F1, F2, and F3 in a decreasing order. We will illustrate stage 2 Nash equilibrium given the F3 as a constant. And notice that our model can be generalized. Consider the totally I fee choices, and here is a simple illustration. So the stage 2's Nash equilibrium reflects users' trade-off between transaction fee payment and waiting cost. In this figure, there are totally 3 equilibrium: F1NE, F2NE, and F3NE. So F1NE happens when the F1 is low. Then all the users will choose the highest fee choices F1 to minimize the waiting time, which corresponding to this case. This exactly happens when F1 is low. And when F1 is large but F2 is low, then all the users choose medium fee choices F2, such that they avoid the high fee payment of F1, but they choose the medium fee to lower their waiting time. And when the F1 and F3 are both large, then all the users will choose the lowest fee choices F3. This is to avoid the highest. This is to avoid the high fee payment. So after stage 2, we consider the protocol designer's mechanism design. So there are 2 decision variables for the protocol designer. First is fee choices for the users. There are totally I fee choices. Second is a waiting tax for the users. There are 4 waiting tax. We call our mechanism as FWT mechanism, which is fee choices and waiting tax. The FWT mechanism, the objective will be the social welfare maximization. The constraint of the optimization problem will be the storage sustainability constraint, where we want the average transaction fee of the users is able to be covered the transaction's storage costs. Here, the objective will be the social welfare maximization. The constraint will be storage stability, and the zero variable is as follows. The next come to the optimal mechanism of the stage 1. So we'll first define the unconstrained social optimal, where we maximize, this is to define as the maximizing the social welfare without the storage sustainability constraint. So our FWT mechanism is subject to the storage sustainability constraint. So in general, it will achieve a smaller feasible region compared with the unconstrained case, because unconstrained do not need to consider that constraint. Intuitively, our mechanism will have lower social welfare due to a smaller feasible region. But surprisingly, in theorem 2, we show that our optimal mechanism achieves the unconstrained social optimal. This result helps to answer the key question 2, where it shows us how to design a storage sustainability mechanism for heavy users. Our FWT mechanism satisfies the storage sustainability while achieving unconstrained social optimal. So because that we have the fee choices that encourage users to pay the sufficient fee storage cost. And on the other hand, we have waiting tax to let each user pay for the transaction congestion and avoid the long waiting time. And next is some numerical results. First, we illustrate the social welfare regards in the waiting cost factor gamma and the transaction on-chain utility. So the result shows that our mechanism improves the social welfare by 51% compared to the current blockchain practice. Next, we illustrate the transaction waiting time of the mechanisms. So we consider compare our mechanism with the current blockchain practice. We consider the transactions average waiting time and the bottom 10% fee transactions average waiting time. We find that our mechanism reduced all transactions average waiting time by 62%. And reduce the bottom 10% fee transactions by 69%. We find that our mechanism will favor the bottom 10% fee transactions by reducing the waiting time out further. This is because that our mechanism reduces the number of transactions by the waiting tax. So the lower fee transactions will face because the low fee transactions face many higher priority transactions, so reducing the transaction number is more significant for them. So this concludes for the first part of the presentation. We find the reason of storage sustainability issues where the miners neglecting the negative externality of transaction selection. Such that each miner select transaction when the fee can cover his storage costs, but it can be far away from cover all miner storage costs. Second, we propose a storage sustainable mechanism for heavy users. We use fee choices to encourage users to pay sufficient transaction fee, and we use the waiting tax to let each user pay for transaction congestion, avoid long waiting time. And this mechanism achieves both storage sustainability and unconstrained social optimum. And the second part of this talk considers the let user setting, where each user generates one transaction and decides its transaction fee. So for the part two, the motivation is as follows. We will consider some additional features of the blockchain. First is heterogeneous storage cost miners. Under this case, miners can have different storage cost consumption. For example, in the Ethereum, in the archive nodes, the storage cost is about 10 times larger than our full nodes. So this will lead to very different storage costs for the miners. Moreover, in a shared blockchain, some miners can store one shard of data, while others may store multiple shards to support cross-shard communication. This will also lead to different storage costs among miners. Second factor is the transaction expiration. We consider a pending transaction can only be included in blockchain before its expiration time. So this is because that the Bitcoin's course default transaction expiration time is 2 weeks from the transaction's generation. So regarding this, our key questions as follows in part two. So first is how do heterogeneous storage cost miners select transactions? Second is considering their strategies, how to design a storage sustainability mechanism considering the transaction expiration under the let user setting. So our mechanism, storage sustainable mechanism as follows. First, the mechanism will assign the fee lower bound F underline, which is larger than 1. So specifically, the system will denies any transactions with fee below F underline. In the current blockchain system, the F underline equals 0 and causes a storage sustainability issue. So we want to set this fee lower bound to encourage users to pay sufficient transaction fee for the storage cost. Second aspect is the transaction expiration time, which is an integer, where we want the transaction to expire after T blocks from its generation. And this is also a general model that can characterize many blockchain systems. For example, if the T approaches infinity, this is the majority of the current blockchain practice. So again, we use a 3-stage Stackelberg game to characterize the model, characterize system. In stage 1, the system designer designed the mechanism. So he will decide the fee lower bound and decide the transaction expiration time. In stage 2 is user's transaction proposal. So he will propose, users will decide the transaction proposing probability and set the transaction fee. In stage 3 is the miner's transaction selection. Mining each block, miners select transactions to be included in blockchain. So again, we will introduce and analyze the system model backwardly. So because there's some similarity regarding this model, and the part 1's model, so here we will skip the similarity details and only focus on the key difference. So for the key difference of stage 3 is the heterogeneous storage cost per transaction. In part 1, we consider the homogeneous case, but here we generalize to the heterogeneous scenario where the CM represents the storage cost per transaction. It can have 2 types. When miner M is a high cost type, it equals to CH. When it's low cost type, it equals to CL. So based on the model, we can derive the stage 3 Nash equilibrium. Specifically, the miner M will select transactions with fee above the threshold delta M tau during mining block T. Specifically, the delta M tau equals to follows. So This theorem 3 helps us to answer the key question 3, which is how heterogeneous miners admit transactions. So for the low-cost miners, we find that their fee threshold will be a constant regarding the transaction expiration time. But on the other hand, for the high-cost miners, their fee threshold decreases as the transaction expiration time increases. This is because that as the transaction expires later, the low-cost miners are more likely to include low-fee transactions in blockchain. So this forces the high-cost miners to admit the low-fee transactions, such that they will bearing the storage cost, but probably getting some transaction fee. And also the theorem 3 also explains the zero-fee transaction in blockchain. Some miners store very few data in the blockchain system. Specifically, they will run in the SPV mode, and they will have close to zero storage cost, which means CL is roughly equals to 0. Such that all miners' fee threshold will be 0 given the current blockchain's mechanism parameter. So the miners will include the zero-fee transactions in the blockchain, and that is also confirmed by the Dwarf pool and UU pool in the Ethereum. And regarding the zero-fee transactions, this gives users little incentive to pay sufficient transaction fee for storage costs. Since zero-fee transactions can also be included in blockchain, this also worsens the storage sustainability issue. Next, we reach the stage 2, which is users' transaction proposal. We consider there are totally n light users, each makes decision on one transaction. So strategy for the user n is proposing a transaction with probability Pn, and when proposing the transaction, he will also decide his transaction fee payment method. The payoff is denoted as Pn multiplied Vn, where Vn is a utility from the transaction n. Specifically, the Vn takes two values. If transaction n is in the block P, the user n gets the transaction on-chain utility R, pay the transaction fee, and bear the waiting cost. On the other hand, if transaction n is not in blockchain after T blocks, then the transaction expires. So the user will bear the transaction expiration loss A. And here we assume that here for the transaction expiration, it means that the user's waiting time is not larger than T blocks because the transaction expires after T blocks. Then we illustrate the stage 2 Nash equilibrium against the high cost miners threshold, delta H, sigma H, and the waiting cost factor gamma. So here is a figure illustrating this. There are totally 3 types of the Nash equilibrium. So we find that as the transaction fee and the waiting cost increases, the users propose fewer transactions. First is when the waiting cost factor and the fee threshold are both small, users will have the all NE equilibrium. This means that each user proposes one transaction. And when the threshold and the waiting cost are medium, each user proposes transaction with a probability, and this will reach the partial NE. And when the threshold and waiting cost is high, the no user will propose transaction and we reach the non-NE. Next, come to the stage 1, which is the protocol designer's mechanism design. The design variable are the fee lower bound and transaction expiration time. The objective is the social welfare maximization and storage sustainability. So despite the this maximization problem is integer programming because transaction expiration time is an integer, anyway, we are still be able to derive the closed form solution for this mechanism design problem. So the our optimal mechanism design solution is as follows. This helps us to answer the key question 4, which is how to design the how to design the storage susceptibility mechanism with the transaction expiration. For the optimal fee lower bound, this is a transaction's. This is exactly a transaction's total storage cost for all miners. This ensures that each transaction's fee can be covered the transaction's total storage cost, guarantee storage sustainability. Second is the transaction expiration time is finite. As T star, we find that when there are many users generate many transactions, some transaction will expire because of the existence of transaction expiration time. Based on this, we define the corollary 1, which is a transaction expiration. So under the optimal mechanism, it lets some transaction expire, achieving a higher social welfare than the never expiration mechanism. So this result is interesting to show that the mechanism deliberately lets some transaction expire to achieve higher social welfare than the current blockchain practice, which the transaction never expires. This is because for the transaction expiration time, it indeed lets the user spare the transaction expiration loss. But on the other hand, the user's transaction waiting time will be lower than the T-star block. This is because the transaction expires after T-star's blocks from the transaction generation. So when there are many transactions, waiting time is high, then the transaction expiration is better than waiting all transactions being included in blockchain. We also implement a Bitcoin-based blockchain testbed and compare our proposed mechanism with current practice. First, we illustrate the transaction fee regarding the transaction fee and the impatience level, and the transaction fee as the number of users. We find that our mechanism can ensure users pay sufficient transaction fees, and also we find that when users have higher impatience level, and they may still pay a lower transaction fee, because that when they have higher impatience level, they will bear higher waiting costs, and this also may prevent from users from generating many transactions. Second, we illustrate the results on social welfare. We find that our mechanism achieves about 56% higher social welfare than current blockchain practice. So this summarizes part 2 of this talk, where we propose the heterogeneous storage cost. We find for the heterogeneous storage cost miners, as the transaction expiration time increases, high-cost miners are willing to accept low-fee transactions, and we also find that zero-cost miners cost zero-fee transactions. For the storage sustainability mechanism, we find that when there are many users, transaction expiration can increase the social welfare due to the reduction of the waiting time, and our experience shows that our mechanism can increase about 56 social welfare. So the conclusion of this talk is that we find the reason of storage susceptibility were miners neglecting negative externality of transaction selection. And for the heterogeneous storage cost miners, we find that as transaction expiration time increases, high-cost miners is willing to select lower-fee transactions. Moreover, we find zero-cost miners cost zero-fee transactions, and we propose the storage sustainable mechanism, which can also enhance the social welfare For the heavy user setting, we propose fee and victim tax mechanism. For the light user setting, we propose fee and transaction expiration mechanism. Some future works in the storage sustainability mechanism in blockchain is as follows. First is incomplete information. So currently we assume that some of the information is known by system designer, for example, the impatience level, transaction on-chain utility. But in reality, this information is likely to be unknown by the system designer. So we also need to consider how to design the mechanism under incomplete information scenario. Second is how to compensate for future miners' storage costs. So in the blockchain system, miners will join and leave. So a user generates transaction currently. How can he compensate for future incoming miners' storage costs? So this is also a topic that need to be considered. Third one is a mechanism to encourage miners to store multiple shards of the data. So in the third blockchain, some miners need to store multiple shards of the data to support cross-shard communication, but currently there's no incentive mechanism to encourage them to do so. So we also may need to propose a mechanism to achieve this goal. And the publication of this work is as follows. So this work has been accepted in IEEE Communication Magazine and also been published in JSAC and the TOM. And also we have published our paper in the ICC. And this concludes my talk. Thank you.
Thank you very much for the wonderful presentation. I learned a lot. This is not my areas of expertise, so I think mostly I was just learning. And if you have any questions, please reach out either to me or either to Yunshu. So Yunshu, how can we reach out to you? Do you have an email address or a phone number or something like that?
I will type my email at this chat box.
Okay.
So my email is okay. So this is the email of my of myself, and also
okay.
You can find also you can find my email in the regarding all the papers presented here.
Yeah. Okay. Great. Yeah. Okay. So we are on top of the hour, so I guess we can just leave it at that for today. And thank you again, Yunshu, for the wonderful presentation. I will upload your presentation to our website so that people who are not able to join today will watch it online. We look forward to learning from you in the future.
Okay, thanks.
Thank you. Bye-bye.
Thank you, bye-bye.